Welcome to Spring LIB.
Okay, this is kind of a long one, but that's okay. We've got the reaction between this tertiary iodide, haloiodide, or alkyl halide, undergoing an SN1 reaction to give water or like a protonated alcohol and iodide. And we need to draw a mechanism for this reaction. Okay, first of all, iodine leaves, right? We get a tertiary carbocation, and water will attack to give our protonated product. Okay. Now we need to draw an energy diagram for this reaction. Okay. And we're told that we're doing delta H. And this is going to be reaction coordinate. Okay, it's a two-step reaction. We've got starting materials, we've got our carbocation intermediate, and we've got our product, which we're told is at the same energy as our starting materials. And if it's a two-step reaction, then we know we're going to have two transition states. We also know that because it's SN1, the barrier for the first transition state should be larger than the barrier for the second transition state. Okay. So EA is going to be this first barrier, the activation energy. Draw the structure of any transition states. So we need to draw a transition state of iodine leaving, right? So we'll just draw some, I think we'll do something like this. Dotted line to iodine. These are methyl groups. Okay. Double dagger on the brackets to indicate it's a transition state. Iodine will become negative, so we put a partial negative there, and partial positive on the carbon, which will become the carbocation. And then for the addition of water, we need to draw a partially planar, or sorry, a planar intermediate, right? So we should have something like this. And we should show water coming in. This water is not partially negative. It's partially positive because it becomes partially positive. And this carbon goes from being partially positive to neutral, so it should be partially positive. And we'll need a positive sign up there. Okay. So what is the rate equation for this reaction? Well, recall that if it's SN1, that means the rate equation should only depend on the iodine leaving, right? So, meaning that the concentration of the substrate is all that matters, right? So the rate equation should be rate equals K times the concentration of our substrate. Okay. So what happens if the leaving group is changed from iodine to chlorine? Well, chlorine is a worse leaving group than iodine, and the rate equation depends on the strength of the leaving group, right? That's what this is here. So if iodine goes to chlorine, then the rate will go down. What if the solvent is changed from H2O to DMF? Okay, so H2O is capable of hydrogen bonding. DMF is polar but aprotic. But if you were or weren't aware, carbocations, which is related to the height of this intermediate as well as this transition state are stabilized by polar protic solvents, right? So if we move from polar protic to simply polar, then the stability of our carbocation intermediate will decrease, okay? Meaning, sorry, decrease would be up. The stability of our carbocation intermediate would decrease, meaning the transition state energy would also increase, meaning our activation energy would increase, meaning the reaction would go more slowly. So once again, the rate would decrease. Finally, if the alkyl halide is changed from, I believe what it's saying is this to this, would the rate change? And here the answer is CH. Yes. Okay, that's what it would change to. And here the answer is yes, right? Because we've got to go through this secondary carbocation intermediate in that case, right? Once again, we'd be decreasing the stability of the carbocation intermediate, okay? And the rate would decrease. Finally, if the concentrations of both the alkyl halide and the H2O are increased by a factor of 5, well, the water doesn't matter, but if we increase the concentration of the substrate by a factor of 5, then the rate will increase by 5, right? We're just saying multiply this by 5. We're also saying multiply water by 5, but water does not appear in this equation at all, so it won't have any effect. Meaning we're not going to do like times 25, we're just going to be doing times 5. So the answer to that one is that the rate will increase by a factor of 5. We'll get 5 times the reaction rate.